Today we're going to be talking about topic 5 of IBHL Computer Science, Abstract Data Structures. Our focus today is going to be on arrays, stacks, and queues, and we're going to cover points 5.1.4 through to 5.1.10, which are all about how we can use arrays to store, access, and manipulate data through 2D arrays, stacks, and queues. So to start, what is a 2D array? A two-dimensional array, or a 2D array, is like a table with rows and columns. Think of a chessboard or a spreadsheet. These are real-world examples of 2D arrays. Each element can be accessed using two indices, the row and the column. For example, A33 accesses the item in the third row of the third column, assuming we're using zero-based indexing. It's called an array of arrays because each row is actually its own array. In languages like Java or Python, that structure is flexible. But in lower level languages, the size might be fixed. If we take our example of 3, in this example down here, if we go the third row, so 1, 2, 3. Oh, hold on, that wouldn't work in this because there's not enough items. That's my bad. Moving on, we're going to be looking at constructing algorithms using 2D arrays. So here we have a 2D array traversal. When we want to perform an operation on every element in a 2D array, we need to use two nested loops, one for the rows and one for the columns. Like we can see here, we have our outer loop, which loops from 0 to the length of A, and the second loop, which loops from J to the length of A, taking the account the value of I from the loop it's inside of. Let's say you want to sum all the elements. You'd initialize a variable sum. So let's say we had an array that looked like this. So if we did sum and we called this loop, we could use this to loop through it, and we could edit this algorithm to do some sort of sum calculation. Then it would add each element as we went on. We could also check for specific conditions such as how many values are even or how many are greater than a certain threshold. These patterns often come up in paper 2. Now we're going to look at the characteristics and applications of a stack. Stacks are LIFO structures. Last in, first out. Picture a stack of books, like I'm drawing here, inside of a box. When we put in our first book, and we put the next one on top of it, it can be accessed. Our book number 1 cannot be accessed until we take out book number 2. That is essentially how a stack works. You add to the top and you remove from the bottom. The two main operations that define a stack are push, which adds an item to the top, and pop, which removes the top item. There's also isEmpty and isFull, which just checks if the stack is empty or full. The stacks are used in backtracking, undoing or redoing in a software, and tracking recursive function calls. Even the call stack in your computer is a stack. They're simple but powerful because of how controlled the access is. You can only deal with the top item. Now we're going to look at the pseudocode for stack. So to implement a stack using arrays, we only deal with the end of the array. As we can see here, our pseudocode, we have a function for push and a function for pop. This implementation is static, meaning once the array is full, we can't push any more unless we resize the array, which is beyond the IB specification. If the array is full and we try to add another item, we get something known as a stack overflow. And in the same case, if the stack is empty and we try to pop something, we'll get an error called a stack underflow. This occurs when you try and pop or push items to a stack without checking if it's empty or full. Now we're going to look at queues and the characteristics and uses of them. Queues are FIFO, first in, first out. Think of a supermarket line. The first person to arrive is the first person to get served, and therefore the first person to leave. There are two core operations when it comes to a queue. NQ, which adds an item to the end of the queue, and DQ, which removes an item from the front. There's also isEmpty and isFull, which we had covered in stacks, which do the exact same thing. The uses of a queue include scheduling tasks for your CPU, printing tasks, or order systems, such as ordering food on a self-serve at a restaurant, or when you go to a supermarket and you go to the checkout. They're vital in real-time systems because they maintain order. If we look at the algorithm for a queue, when using arrays to implement queues, we have to keep track of the front and the rear. Here's a simplified version, assuming we always remove from the start. Like in the stacks, this is the two main function, which is NQ and DQ. And if our queue is full and we try to add another item, your queue will return something such as queue full. And if your queue is empty and you try and remove an item, you'll get a similar message. The problem here is that removing from the front requires shifting all the other items one place forward, which isn't efficient. Just remember, for queues, you always add to the end, remove from the start, and check if the queue is full, because if it is, you won't be able to add any more to it. Now we're going to look at arrays as static structures. In all the implementations we've done so far, arrays are used to build stacks and queues. But arrays are static structures. They don't grow or shrink. That means for stacks, we may hit a stack overflow if we push too many times, or an underflow if we try to remove or pop too many times. And for queues, we may hit a queue full if the rear pointer reaches capacity. In real software, we'd use dynamic structures like linked lists or dynamic arrays. Just make sure to remember that it's a fixed size. You may reach an overflow for the reason that it's static, and you cannot resize them unless that data set is being replaced.